Okay. Make sure this is working. Blended. Okay. Don't write anything. Just look at the board. That's all eyes on the board. Okay. We're studying how to find antiderivatives. Don't write anything. We're studying how to find antiderivatives. The study of how to find antiderivatives is actually quite complex. It takes a lot of time. So most of that study is done in Calc 2 or BC calculus. We only do a tiny bit, just kind of an introduction. So what I'm teaching you really just applies to this class. If you were to take Calc 2, you're going to have to expand your vision a little bit. Understand what I'm saying? Okay. So here's a pattern you're going to want to look for when you're trying to find an antiderivative. Let's just look at the board. So these are the problems that you worked in the homework. And they all have a specific pattern that you may not have noticed. But I need you to notice the pattern now. The 5 is a multiplying constant. The function is cosine x. Okay? So 2 key things. 1, cosine x has an exact match as a rule. So that's why you were able to do it. Next one. 2 functions are adding. We learned that doesn't really matter. We can just find the antiderivative separately. So looking at them separately, 18 is a multiplying constant. X to the 5th fits the power rule perfectly. X to a number. So that's why that worked. Okay? Next one. 5 over x. Well, that's really 5 multiplied by 1 over x. And once again, 1 over x fits the rule perfectly. It's getting kind of boring now. Cosine. Let's go look at, those all have the same pattern. There's something new. The first difference is you no longer have a single function. You have 2 functions being multiplied. There's an extra multiplying constant, negative 24. The first function fits the rule just great. That would be, the power rule, x to an n. This doesn't fit the rule at all, because that's not e to the x. It's e to the mess, like e to the bunch of stuff. So that doesn't fit the rule. So today we're going to talk about how do we handle that situation. And you'll notice that every single problem I asked you to skip has a similar form. 2 multiplying functions, 1 or both appear to be a lot messier than what you worked with. Like look at this one now. Oh, back to simple. Multiplying constant, simple function. Number 10, hey, 3 simple functions being added. Number 11 is, let's see, hey, that's just negative 12 times 1 over x to the 4th. And we change the x to the 4th to x to the negative 4. We have back to using the power rule. Go to number 12, though, we run into a mess again. Just a lot more involved. Okay? The key difference is simple functions like this versus 2 multiplying functions that are more complex. Okay, so for our class, you need to make that distinction. Like when I told you to skip certain problems, that's all I did. I just looked down the page and said, okay, where are the functions being multiplied? Because I know that's going to require a different technique. That's all I did. Questions so far? Sweet. So let's work on that. So write number 12 on your paper if you haven't already. And we notice right here that we have 2 functions being multiplied. As like with derivatives, as you work these types of problems, you'll get better and better at solving the problem without having to write so much. But in the beginning, it really helps if you write a lot, so you don't get confused. And then as you get better, you can write less. So everyone's going to write on their paper, and this is the same thing I said with derivatives. So eyes on me. If you don't show your work the way I show it, no retake and no help. It's just way too hard. When people invent their own little method, it's not necessarily wrong, but it's just too hard for me to help. So do it the way I'm doing it. So first thing is you recognize that's complex. It's not one simple function. I can't just use a rule. So I want to write it as two functions being multiplied. So raise your hand if you can tell me, how would I write that thing right there as two functions being multiplied? So I've got my antiderivative sign. I want to write it as two functions being multiplied. Hands up. All of them. Come on. Amelia?
Do 12x over 1 and then multiply by the antiderivative of 1 over 2x squared plus 1.
2 points for Amelia. 1 point if your hand was raised. Her thinking is very good. There's one thing we can't do. We can't make two antiderivatives.
Okay.
So that's illegal. Don't ever do that. Like when two things are adding, yes, you can split it. Multiplying, no. So they stay inside the antiderivative, and you write it like so. But the thinking was very good. So that's the first step right here. I want two functions that are being multiplied. And again, with practice, you can do that step in your head. Okay? Questions? Always go straight down the page. Next thing. What I know, this isn't in my list here, but I like to factor out multiplying constants if possible. So please raise your hand if you have any trouble seeing that this, like if we were to multiply that 12 over 1 straight through, raise your hand if you're comfortable that we would get the exact same thing we started with. Like if we take this 12 over 1 and we multiply it straight across, raise your hand if you're comfortable that we get that. Hands up, you can see it. Point, okay. Questions?
If we multiplied the 12 all the way across, would we have a 12 over 2x?
Over this one?
Yeah.
2 points for Taryn. I want to do something in hopes that it will answer your question. If it doesn't, we'll keep talking. So Taryn, if you saw this, what would you write?
24.
Good. And you did it by doing what?
4 times 3, 12 times 2.
Good. So you never double multiplied.
Yeah.
Like you didn't take the 4 times the 3 and the 4 times the 2.
Oh.
So same thing here. You've got 1, 2, 3 things to multiply. Does that make sense? You just pick. It's well done. 2 more points. Anybody else? Okay, cool. Okay, first thing, we split it. We've pulled out a multiplying constant just to make life easier, because this multiplying constant now, we don't have to worry about it. It just follows. We don't do anything with it. It just follows, okay? Next thing, we have 2 multiplying functions right here. Okay, the reason we have 2 multiplying functions is because, I'm going to cheat on you here, we started this whole idea with something that we can't even see. What we started with was, so on your, this is your paper, way over here on the right, please write down the following. Derivative of 3 natural log 2x squared plus 1. Plus, I don't know, say 8. Over dx. Okay, question. Okay, so you don't know this, but what we started with was this green thing. And we're going to take the derivative of this green thing. So I need someone to raise their hand and talk me through the derivative of the green item. So someone volunteer to tell me what I should write.
3 over
So Kate knows 3 is a multiplying constant, so she writes that down. She then says the derivative of the natural log of something is 1 over that something. Keep going, Kate.
Plus
You forgot one step.
yeah, sorry. D of 2x squared plus 1 over 6.
So multiplied by the derivative of that something. And then plus 8 means we take the derivative of the 8 alone. Kate, what would be the derivative of the 8 alone? 0. 2 points for Kate. 3 actually. 4. Mark down 5. You're the only one who raised your hand in the whole room. Questions? Okay. Here's what I'm trying to get you to put together, like as a big idea. Is what really happened here is you started with this formula here, and I'm now parenthesizing, and let's do it in yellow. So if you start with a formula like this, and you take the derivative, you get this item here. Let's go one more step. Raise your hand, please. What am I going to replace this right here with? Looking for hands. What's that going to be replaced with? Hands up. So I have the 3. I have the 1 over 2x squared plus 1. And I have that thing. What's that going to be? There we go. What's that one, right?
4x.
Please raise your hand if you knew that was 4x. Point 2 right. Okay, so what I'm trying to get you to see is this. If we start with this formula here, and we find a derivative, we're going to get this item here in blue. And what I'm trying to help you decipher is that's what we have over here. Okay? The blue box here is not exactly the blue box here, but I'm hoping you can see that they are essentially the same thing except for differences in multiplying constants. In fact, if we take out the 3 and the 4, we have exactly the same thing. So put those together, there's the 12 right there. So that's the idea. I'm trying to find the antiderivative of this. Well, that's going to become this right here. I just got to figure out how to do that. Questions? Okay, so first thing to recognize is I keep talking about the fact we have 2 functions being multiplied. 2 functions being multiplied. Well, the reason we have 2 functions being multiplied is because when we took the derivative of this thing, this wasn't 2 functions being multiplied. But when we took the derivative, the chain rule required that we end up with 2 functions being multiplied. So if we're starting our antiderivative with 2 functions being multiplied, it's a huge clue that, hey, maybe that came from the use of the chain rule. That's the whole idea. Questions so far? So that's the big picture of where we're trying to unravel this mess. Okay, the trouble is you don't know this. You have to figure that out. Okay? So the method for figuring that out is as follows. Let's get rid of this. Pull this out of the way. It's to recognize that when you use the chain rule, it's always, you're taking the derivative of something like this, and then the last thing you do is you take the derivative of what's inside. You're taking the derivative of something like this. The last thing you do is you take the derivative of what's inside. Same thing here. So up here, we had 3 times the natural log of this thing that's inside. And then we took the derivative of this thing here, That's how we got this 4x, like that. So, what I have found works best to unravel all this stuff is to do the following. I recognize that I have two multiplying functions. I've already done that. Now I need to recognize that those functions have got to fit my rules. So look at your salmon sheet and notice there are only 5 rules. There's 5 rules and there's the expanded version. Look at my board and notice this is the first rule, power rule, exponential rule, ln, sine, cosine. So that's where you begin your thinking is, okay, I've got 2 multiplying functions. I've got to see how they fit my antiderivative rules. So I notice that the very first one here, x, that fits the power rule. X to the first. X to the first. The second one fits the ln rule, 1 over something, like that. What we're going to do now is what's commonly known as a U substitution. It could be called a W substitution, a Z substitution, whatever. U is random, okay? I like using U because it helps me tie it to a movie I really like, and I'll explain that in a minute. Plus, that's how I was taught. So please write on your paper now. So we've got this stuff going straight down the page. We have our little notes over on the right, and now right here in the middle we're going to put the following. We're going to write U is equal to, we look at our first multiplying function. The first,
Miss?
yes,
Mariel Sutton is being checked out.
okay.
You.
The first function is x to the n. So the something there is just x. So we'd always pick the u as the something. Write that down. We go to the second multiplying function. And we notice for the second multiplying function, that's this one, 1 over something. We always pick the u as the something. So u is going to equal 2x squared plus 1. Questions? Here's why I say it ties to the movie. I really like the movie The Help. Has everyone seen the movie?
Great fun.
Yeah, that's really good. I haven't read the book. I should do that. The movie's very good. And in the movie, if you know the movie, you know there's the maid who takes care of the little girl, and she has the little ritual, right, of every day. She sits down with the little girl and she says, remember, you was smart, you was kind, you was beautiful. I remember, you was beautiful, you was special, you is something. I know it's not very funny, but try to remember it. You is something, okay? The U is always the something.
How can you have the U equal 2 different values?
Listen to Maddie. It is not possible for U to equal 2 different values. So what I'm teaching you is a way to determine which one is correct.
Okay.
So you have 2 multiplying functions. Now I have to caution you. We will see problems in the future where we don't really have 2 multiplying functions, and this U substitution technique will still work, but it's kind of an exception. So if you can learn this method, then you're pretty good for the exception. So no, you can't be 2 different things. But we have 2 multiplying functions. So after the movie The Help, we have 2 somethings. So U is something. It's either this something or it's this something. And I'm going to show you how to figure out which one. Then we'll cross off the other one.
Okay.
We just don't know yet. Everybody good? Points for Maddie. Okay, the next thing you do is you apply the derivative operator to both of your choices. That means you take this equation here and you apply d over dx to the left-hand side. So that means you get d over dx of u. But to maintain equality, I have to do the same on the right. D over dx of x. Write that down. Questions? Okay, don't overthink it. Please raise your hand and tell me what belongs in this box. Hands up. Don't overthink it. Everyone's overthinking it. Staring right at you. What goes in the box, Michael?
1.
How many agree? Point. 2 for Michael. Okay. Now we do the same thing to our other choice of U. So I didn't leave my spacing as well as I would have liked. So I'm going to see if I can fix that without erasing.
I wish I could do that.
Hey, it worked. Often does not work. So now I apply the derivative operator here. So I get du over dx is going to equal d of 2x squared plus 1 over dx. So running out of room here, so we'll go like so. Du over dx. Hands up, please. What gets written here? Hands, come on. Everybody think, don't just watch. What goes there? So Brooke Greenwood. Sorry, I looked there and looked at Brooke Hunter. My apologies, I owe you both a ticket. So I looked straight at Brooke Hunter and said Brooke Greenwood. Yeah, and that's why they both froze. Like, wait a minute. Go ahead, Brooke.
4x.
Please raise your hand if you knew that. Point 2 for Brooke. Okay, so back to Maddie's question. We got to figure out which U actually works. Here's how you know. You come back over here and think, okay, where did this all come from? It came from the fact that I was taking the derivative of some formula, and when I took the derivative of something, that's when I created the other multiplying function. So notice the pattern. If U is this, if this is the correct something, the derivative of the something is supposed to be the other multiplying function, because that's how it was created when you did the chain rule. You had a something, you took the derivative of that something, the derivative of that something became the other of the two multiplying functions. So the something came from one of the multiplying functions, the derivative of the something was the other multiplying function. That's what you're looking for. This one works. If that is my something, right here, the derivative of my something is the other multiplying function. So this was the correct something to pick because that derivative becomes the other multiplying function. You don't care about the constants. They can be manipulated easily, the multiplying constant. The derivative of 2x squared plus 1 is 4x. There it is. Questions? The other way around wouldn't work. If this is my something, I get a derivative of 1, but that's not this. That doesn't follow the pattern. This idea of U substitution is trying to undo a chain rule derivative. That's what we're doing. Questions about anything? Please, Amelia.
So when you say chain rule, like, I just don't understand, like, how is this one a chain rule?
Gotcha. So flip your sheet over. Look at the green sheet. Amelia's question is not quite remembering why this is the chain rule. I totally get that. It appears that right here I'm using the ln rule. Is that correct, Amelia?
Yeah.
What is often forgotten, and I don't honestly do a great job explaining it, is the last portion of that ln rule where it says find the derivative of the something. That's actually there because of the chain rule. So every single rule has the chain rule built into it. Most textbooks don't teach it the way I teach it. I like my way better because it's my way. Might as well be honest, right? I do think it's more effective. I think it's faster. But I give you the rules with the chain rule already built in. Does that help a little?
Yeah.
2 points. Anybody else? Please, Rich.
So let's just say that the 4x was actually 4x squared. Would that not work anymore? Because over on the other side it's x.
Everybody look. 2 for Rachel. That is dead perfect. Because again, the idea is I'm trying to figure out what happened when I did the derivative. And the hard part is you don't see anything over here, right? You don't know this. So Rachel's correct. If I make my choice for something, and I take the derivative and it isn't the other multiplying function, like it's 4x squared, it doesn't match this, that means U substitution won't work. Now, good news for our class, you don't really get tested heavily on antiderivatives. So it's either going to be a simple rule, like that. If it's a U substitution, it has to work. Otherwise, the only other alternative is maybe there's a little trick, and I'll show you a couple of tricks. They're just simple, that will work instead. Anybody else? Please.
Can you explain how we know that like the U equals X can be substituted?
So the basic pattern you're looking for is you have 2 multiplying functions. You good with that, Kate?
Yeah.
You're going to pick from one of them a something. The something comes from how we use the derivative rules. Like right here, something to a number. 1 over something. So the something I pick would be just the x. But that means that when you took the derivative of that something, that's how this other multiplying function was created. It was created by taking the derivative of this something. But the derivative of this something isn't the other multiplying function. So it doesn't work. The other way does work. Does that make any sense? 2 points. Let's try another one. Don't write anything. Just watch for the pattern here. Look at number 13. Oh yeah, Isaac, question.
Wait, so we can't solve that one?
This one here?
No. Yeah.
No, this one works. We can't go that way. We can't do this. This is wrong. We can't say the something is x.
Yeah.
But we can say the something is this.
But how do you know that something is that? Because you don't know the answer.
We don't, but we know that if we choose this as our something, the derivative of our pick is this. And that's enough to prove to me that if I do some more steps, it's going to work. Because it's enough to me to reveal that where this all came from was this was the result of finding the derivative of, basically it's right here. It was this. Well, I don't have the right, well, I need to put the derivative rules on. We used the ln rule to find the derivative.
Yeah.
So we're going to use the ln rule to undo it.
Yeah.
But the extra thing here is coming from the fact that when you use the ln rule, you have to find the derivative of this something.
Okay.
Stay with me. I think it'll clear up in a second. Let's look at some more patterns. Look here. Let's go back to Kate's question. Okay, look. Raise your hand if you can see the 2 multiplying functions. Come on, who sees them? What are the 2 multiplying functions, Spencer?
The 40x and the 4x squared was 3 in parentheses to -4.
Okay, so please raise your hand if you honestly would have said, we got 40x multiplied by this. How many would have said that? 2 points, 3 for Spencer. Okay, look at my little notes here. The 40, ignore the 40, that's going to factor out. So we have x, that means we have something to a number. So in the first multiplying function, hands up, sorry, that's circling wrong. The 40 we're going to factor out. So in the first multiplying function, hands up, what is the something? Don't overthink it. What's the something in the first multiplying function? What's the something? Ben? How many knew that x is correct? Good. Ben, what's the derivative of x? Just 1. 1 isn't the other multiplying function. So that's the wrong choice. Don't choose u equal to x. It's not going to work. So what's the other choice for the u? Hands up. What's the other choice for the u in this problem? We're just kind of trying to get you to see the pattern. Right? Don't write anything. Just watch. What's the other choice for the u in this problem? What's the other something?
4x squared minus 3.
do not include the exponent because you're following this pattern, Taryn. You're looking to say, hey, that fits this form. It's something
Yeah.
to a number. U is always the something. So Taryn, so 2 for Brooke, 1 for the rest. Taryn, what's the derivative of our something this time? Oh, you're okay. 2 points. What is it, Soraya?
8x.
So Soraya, is the derivative of our something the other multiplying function? Yes. We don't care about the 8. 2 points.
So you're saying that we can make the, since it's 8x and that's x, we can make the 40 equal to 8x by taking like a 5 or something instead of.
Say it again, Isaac. Sorry.
So can we like, because that equals 8x and that's x, so it's not 40x. But we
Right.
can take out like a 5.
We can move the constants.
and then it'd be-
Yeah, the multiplying constant's easy to move.
Okay.
The multiplying constant's super easy to take care of. We don't care at all. Super easy. 2 points.
My question is, how did we get the u equals x from the 40x? Because that doesn't.
Yeah, we took out the 40.
Okay, so we took out the 40, and then we're just left with x.
Just left with that.
But it's not x. Or I guess we would say x to 1.
X to the
That's
furthest.
something. Okay.
So the something is just that.
Okay.
Better?
Yeah.
2 points. Other questions? Anybody? Okay, the whole, look at me. Look. Okay, the process, I haven't, like Isaac's question, I have not shown you the rest of the process. The reason we're taking so much time to understand the pattern is the process is easy. The only thing students ever struggle with is making the right pick. Like once you make the right pick, you can just memorize the steps. They're not hard. It's getting the pick that tends to trip people up. So we're just going to practice for a minute getting the right pick. So go to this one. That one's, that's okay. Hands up. Who can see the 2 multiplying functions? What are the 2 multiplying functions? Let's go, Katie, in the back.
100x to the 4th.
And pause for a minute. The 100 we're going to ignore.
So x to the 4th.
X to the 4th. Keep going.
And then in parentheses 4x to the 5th plus 5 to the negative 3. But when you're doing this something, no.
Nicely said. Hands up, who knew? Point 2 for Katie. So, in the first case, hands up, what would be the choice of U? Hands up, come on. For the first, what's the first something? Grace. How many agree? X. Point 2 for Grace. Grace, what's the derivative of X? 1. 1 is not the other multiplying function. So that doesn't work. 1 is not the, that's not where they, like the chain rule would have created the other multiplying function. That didn't work. So what's the other choice of U? Hands up. What's the other choice of U, Riley?
4x to the 3rd plus 5.
Who agrees? Riley? Riley, what's the derivative of our choice of U?
20x.
Careful.
Oh, 20x to the 4th.
There we go. So that's a match. So that's what happened. When we did the original derivative, which like Isaac says you can't see, you did this as part of the original derivative. And you got this. That's where that came from.
So let's think about when it would match to the first one. What kind of number would we have to have as our something in order? Like, for example, would we have a number, or would we have a something that once we found the derivative of that would equal the second multiplying? So if we had a something that once derived equaled 4x to the 5th plus 5, then you would use that option?
Yes.
Oh.
It's not as common. It's usually the simpler version. Please.
Does it have to be 4, like, in theory, you have Karen's like idea, would it have to be 4x to the 5th plus 5, or could it be x to the 5th plus 5?
Technically, I could make it work with x to the 5th plus 5.
Okay, so that.
It makes it a little bit different, but it'll work.
Okay.
Okay, look at this one. Oh, simple rule there, so don't worry about it. That's pretty similar to the earlier one. Let's do one that's a little bit different. Let's look at that one. Hands up. What are the 2 multiplying functions? Come on. What are the 2 multiplying functions? Parker?
Would it just be e to the 4x?
Nicely done, because the 4 being a multiplier, we don't worry about it.
Yep.
Keep going.
And e to the 4x minus 2 to
To the fifth. So you start out by saying, okay, what are the two multiplying functions? How many do? 0.2 for Parker. So what's the something in the green function? Hands up. What's the something in the green function? You just look at the pattern here. What's the something in the green function? Let's go, Julian.
4x.
Okay, hands up. Who knew? Come on. 2 points. 3 for Julian. Julian, what's the derivative of our something?
Just 4.
Just 4. 4 is not the blue multiplying function. That's the wrong choice of u. Your choice, the derivative of your choice, must be the other multiplying function. Because that's how it happened when the derivative was taken. That's where it came from. Questions? So what's the blue u? Okay, rhythm here. What's the blue u? What's the blue u? What u is blue? What blue would you pick for you? This is where we want to invite in the English department and have them just scream in terror. Because u is what? Like, that sounds like the worst grammar ever. So, Riley, what u is? Nice. The blue u is. Oh, wait a minute. What's the u?
E to the 4x minus 2.
There we go. Because the u is the something. Because u is special. U is smart. This is all referred to Riley, by the way. U is special. U is smart. Yeah. You well deserved. Raise your hand if you knew what Riley was going to say. Hands. Come on. Point. 2 for Riley. Riley, what's the derivative of the blue something?
E to the 4x.
Keep going. A little more.
Oh, and then times the derivative of 4x, which is just 4.
Nicely done. You don't really care about the multiplying constant, even though in this case it really does match well. Look right here. That's the other multiplying function. That's the other multiplying function. Please.
So, like, what's the answer?
Gotcha. Okay. Okay, 2 for Brooke. Hold on. Look at me. Right. Okay, so far what I'm trying to do is figure out a way to help you get started successfully. So now we're going to go back and work it through. Michelle, please.
Not quite understanding. Your first multiplier was equal to 4x, and you found the derivative to be 4x.
Okay, so let me say it back to you. So the first multiplying function was e to the 4x. Therefore, the something in that multiplying function is just 4x. Because I've got to make sure it fits one of these patterns, otherwise my rules aren't going to work. So the something was just 4x. And then you tell me the derivative of 4x is just 4. But 4 isn't the other multiplying function. So that didn't work. Just stay with us. It'll sink in. Okay, back to number 12.
Yes.
Searching for the answer. Okay, there's a lot of writing there. I guess we can keep going. So now what happens is we start making replacements. The technique is called u substitution. We are finding an antiderivative by making a u substitution. In reality, we're finding what we're really doing is we're transforming this from an antiderivative that uses the symbol x to a new antiderivative that uses the symbol u. And then we'll use a rule. Please memorize the following statement. You only find antiderivatives using those 5 rules. No other way. Like, that is the last thing you'll always do. You always go to the rule sheet. There is no other way to find an antiderivative other than the rule. This whole u substitution thing is just to get us to a rule. Because none of the rules fit that blue thing. So can't use the rule, so we got to do this little u substitution deal. Okay, u substitution is just using the equal sign. So watch me use the equal sign. I put an equal here. I write down the 12, so that's the same. I have antiderivative. I go, oh, wait a minute. That's just 1 over u. I just replaced it. Because equal means they are the same. So right here, u is the same as 2x squared plus 1. There we go. Please, Rachel.
Was there a reason you switched the X?
The order.
Yeah.
2 points. Good observation. I switched the order because I know from experience that I've got to get from this antiderivative, Rachel, that uses all x's to one that uses all u's. So I've still got to find some way to replace this. So I just grouped them together to make it easier for me to see it. Well done.
I'm confused.
I would not surprise me. This is not an easy thing to pick up the first time, but once you do a little bit, it's okay.
Okay, so I understand that we're replacing u for 2x squared plus 1.
That's all we've done so far.
What about our x over 1?
That's right here.
Okay. Cool.
Are you okay with that?
Yeah.
Because when I multiply, the order doesn't matter.
So, okay, I'm not confused anymore.
Awesome. 2 points. Hey, come on, look. We got to hurry a little bit. Short day. I was always on Wednesday. Okay, I need to replace x dx. And whatever I replace x dx with, I can't have any x's. Only constants and u. Over here is the ticket. Look here. All of you learned algebra. Okay? You all learned how to do something like this. I don't know. No, that's not going to help. Just rearrange that. Rearrange it.
X equals u over 4.
du is divided by dx, right? Say yes.
Yes.
Good. du is divided by dx. So multiply the dx across. It's just du. Du just means the infinitesimal change in u divided by an infinitesimal change in x. Difference in u divided by difference in x. It's just a derivative. So I multiply the dx across. Hands up if that makes sense to you. Like, who sees that as legal? Multiplying the dx across. 2 points. You didn't raise your hand. All the math you've done to this point in your life is all of it. So, you know.
That.
You're okay. I get it. It's
Why
okay.
we're doing that.
Why is fair. Why is fair. But you do see it as legal.
Yes, I see it as fair.
Awesome. The reason I did is now I'm going to multiply both sides by 1/4.
Okay, so this is us just like trying to simplify the x dx, right? You know,
We're trying to get rid of it.
we're going to get rid of it. Okay, then why did we?
You're okay. Your questions are so perfect. Don't worry.
So why did we bring back in our 4x?
I'm trying to get rid of the x dx.
Correct.
I now have a way to get rid of x dx. Because equal means they are the same. So in place of x dx, I may now write 1/4 du. Because they are the same thing. And now what I've done, I'm not to the answer yet, Brooke Hunter, but I'm extremely close. Because I now have an antiderivative that is extremely simple. And it fits a rule. And so that was my goal. Get to where I can get a simple rule to work. Because you have to find an antiderivative using a rule. You have no other way. Questions? Please, Michelle.
Okay, I just want to clarify. We moved the 12 outside of our
Antiderivative.
antiderivative because we found the derivative of it.
No, we just moved that out of the way because it's a multiplying constant. It's easier to get them out of the way.
So it'll just multiply by 5.
Just kind of goes along with it. Yeah. Just a rule. Okay, I gotta hurry. Watch. Okay, first thing. Okay, the attention has been superb. The interaction has been very, very good. Therefore, I went as fast as I could and still feel like I'm not losing everyone. Okay, you're not as lost as you think. I promise. I promise. Look. So don't do any homework tonight. Okay? That means there's only a few people. There's only a few who need to retake. If you need to retake, you need to be coming in like right away, so that you take advantage of this short lull in the homework to get done with the retake. So get in right away. Watch. Gotta hurry. These are just multiplying, so I'm going to do what I did earlier, Michelle. I'm going to get that 1/4 out of the way. Pull it out front. But just say it out loud, please. What's 12 times 1/4? 3. So this is just 3 multiplied by the antiderivative of 1 over u. Please raise your hand and tell me, what is the antiderivative of 1 over u? Hands up. Come on. What's the antiderivative of 1 over u? It's staring at us here. It's looking at you. I have it on the board. What's the antiderivative of 1 over u? ln of u. Absolute value. But use 2x squared plus 1. Look right here. Look. That's the whole idea, is to get to where we started without knowing where you started.
Get out what?
It's okay. The first time my professor showed me this, I had the exact look Taryn has. Like, what just happened? No, I was like you, like, what just happened? Because it works. And Brooke Hunter, this is the answer. Now, they drop the absolute value bars because 2x squared plus 1 is always positive. Then you add on a random constant. You don't know that it's A, you just know it's something. If you take the derivative of the blue box, you get that.
Why did we pick
So much
that as our
sense.
x?
Pick what is our
The
x?
2x squared plus 1. Like, because we know it's the 3 elements of x.
Okay, so this is stupid.
Like, it starts with u.
Hold on, quiet.
Beth, you.
Rachel,
Yeah.
Do you have to write ln of 2x squared plus 1, or did you just put ln?
This is
Outstanding question, Rachel. Okay,
But it makes sense.
look.
Like, all the
Rachel's
things-
correct. Like, I preach that all the time. That when equal means equal, they're the same, right? The reason you have to change it is because the AP test will be, they instruct, like, how do I say this? When they show this, they're telling you they want the answer using the variable x. That's just what the symbols mean. So they want you to switch back. Please.
Wait, and then the du just goes to 1, right?
No, watch.
What is-
Watch. Okay. This symbol and this symbol are just telling you to find the antiderivative of that.
Okay.
So you found it. They both go away.
Well, the u.
They both go away. It's because of equal. This equals that.